So I hope everybody in here has been or is enjoying lunch and some communication and conversations. We are going to move on towards one of the two sessions that were recorded, because this particular one was held in Beijing local time, 1 p.m. yesterday, or 1 a.m. our local time here in the US. Few of us probably made that, so we have this recorded. The question and answer for this session and the one from Australia that we'll see tomorrow is tomorrow at 6, because that's just about when they're back up. So any questions you have, you can put them in Hoover or you can memorize them, and then tomorrow we can actually follow up with the scientists who were delivering the different talks today. So we're very happy that we're able to have a small but in-person meeting in Beijing, organized by Guibin Jiang, who is one of the big fathers of environmental chemistry in China. He's a member of the Chinese Academy, and he is present on a lot of publications linked to PFASs, novel PFASs, and he very gladly, with Ting Ran, took over a session looking at novel PFASs. Given that a lot of the production has moved over to China, there's plenty of things to find about, discover in the environment, and in non-target analysis. So there's a great lineup, and I believe magically the recording will appear here, and it is also on Hoover to watch at any time. That will get us to roughly 4:15, at which stage we move over to local and EE poster sessions, and Kerry McDonough will talk about that, and then we have dinner starting at 6 or so. Thank you very much.
During the past 20 years, environmental scientists from the worldwide try to do our best to understanding the environmental fate, environmental transformation, toxicology, and health consequences of PFOS and PFOA. I think the Chinese scientists will also made our contributions in Chinese environment, try to understand the environmental behaviors as a toxicology, as well as the health consequences. Today's symposium, we have invited 4 professors to talk about their recent progress in this field. Professor Dda he will talk about the environmental behavior and toxic properties of PFCs. Professor Julie Yan, she will talk about some about the new substitute and the progress of our studies of PFCs. Professor Sui will talk about the discovery and the identification strategies for new PFCs. Dda Analysis from our group, she will talk about the instrumental analysis method, and also I think she will talk about the new funding, the new structures from the polar bear. I remember the year of 2004, 2005, during our early studies, we investigated the PFCs, PFOS, PFOAs in our blood in Chinese cities. During that time, we found pretty high concentrations of PFOS and PFOA in our general populations. Fortunately, after 2009, after the limitation by Stockholm Convention, the concentrations from our blood decreased a lot. But with the quickly development of the analytical techniques and also the widely applications of PFCs, the different containers, different species being identified from our environment. To try to understand their burdens, their molecular transformation, their toxicity, property, for instance, endocrine disruptors, and they interfere with the gene expressions, we need more studies. So this symposium, I think as a part of the global FLUOROS conference, we will talk about the recent development in China and how we will join the international effort, try to understand, try to control the pollution caused by Gfos. As so far we understand, Gfos are the most persistent, most polluted. You can find from every environmental samples, from soil, from water, from sediment, our human body and animals. You can detect, you can find Gfos. So for this end, I hope our students, our colleagues, for this afternoon's discussion, you may ask more questions. We may have very good discussions. And I hope the great success. And I wish every people happy this afternoon. Thank you. Thank you very much.
Okay. I think I should say good morning to the audience online and good afternoon to our audience in the room. I'm very honored to have this opportunity to give a presentation to talk about something about PFAS substitutes. This is the first time for me to attempt to take part in this FLUOROS Global Forum. My name is Lingyan Zhu. I'm from Nankai University, and the topic today is about lessons learned from the substitutes of PFAS. Here is the outline of my presentation. As all we know that P4A and PFAS are regulated or limited due to their persistence, fragmentation, toxicities, and other like long-range transportation. For example, the PFAS, the half-life of PFAS in water, it lasts more than 40 years. So these like PFAS and P4A, once they are released into the environment, they could stay there for long time. And then they also might be accumulated in organisms and in humans and induced a lot of various toxicities. And in toxicity, we know that, and the most sensitive toxicity is about immunotoxicity, and also hepatotoxicity, development toxicity. So PFAS and PFA, they were listed in the Annex B and A by Stockholm Convention. So consequently, this regulation prompts the substitutes of them into the market, taking the substitutes of PFAS as an example. As we found, so they include the substitute includes some short chain softening acids. The carbon chain names is less than 6, and the perfluorinated phosphonate acids, and the compound F53B as introduced and talked about just now by Professor Dai. He has mentioned a lot about these compounds because the end atom of fluoride was replaced by chloride, which is much larger in atom size and is also much active than fluoride. Another importance is the insertion of one oxygen in the structure. So MEC is quite different from PFAS. And then another one is the FTS, as just now introduced by Professor Dai. So my talk today will focus on some of them, like short chain and the F53 is quite hot compound. These compounds have applied in many industrial fields, plating, wetting agents, non-stick wells, and fabric for waterproof and firefighting foams. Okay. These compounds, they are used as the substitutes of PFAS or P4A because we hope or we wish they have lower fragmentation potential than PFAS or P4A, for example, because of that short chain, the short chain, or there are other special chemical structures like the phosphate end groups, and we also hope they have no persistence in the environment and display no toxicities. But is the hope can be accomplished by this kind of change? So first, we look at the occurrence of these substitutes in the environment. Our group have continuously monitored PFAS concentrations contaminations in Taihu Lake, which is located in the southeast of China. We look at this figure, we found that like the concentrations of P4 and P4, they vary in a range, not too much. But the concentrations of the short chain compounds, like this one, particularly for the hexane sulfate, increased distinctly remarkably in the last 10 years. And now it became as the dominant compound in Taihu Lake. So this is the result of replacement of short chain compounds to replace PFAS. And we also see the effectiveness of the regulation on PFAS. In the other watersheds, that's like in Taihu River, Tai River, and the middle and the east, the river and the Wei River, the total concentrations of PFAS were lower than that in Taihu Lake, much lower. But the similar theme is that in water, the short chain compounds, particularly for the hexane sulfate, is becoming the dominant compounds. And in some of them, like in this in Taihu Lake is the first one. And in other rivers, it ranked number 2. So this is the change of the harmonics in our surface water. This figure shows the replacement trends. We calculated the concentration ratios of the substitutes or alternatives to P4A and PFAS. And the red dashed line represents the ratio 1. So adding the values higher than this red line means the concentrations was over than P4A or PFAS. So from this figure, we can So from this, we can see the substitutes of the short chain of P4A. The substitute of P4A was mainly these short chain compounds, butane acids and the pentane acids. But for PFAS, there are multiple substitutes like hexane sulfonate, FDS, and F53B. Like in Fan River, FT3B, the concentration was much higher than PFAS. So these suggest the substitutes of PFOS and P4A are very popular in China right now, just because of the regulations on them. And this is one of our work in the coast ocean. Here is the Yellow Sea, very close to Jiangsu province. So this is the Yellow Sea, and we found actually the concentration in the coastal sea ocean still quite high. Is at nanogram per liter, the levels, and similar to the fresh water, we also observed the predominance of some short chain compound like this one. This is the butane sulfonate, and this is the hexane sulfonate. Their concentrations were much higher than PFAS, and similarly, the substitutes of P4A, like the short chain compounds, and here, this is the FTCA, and the HFPOTA. So this is in coast ocean. And then we go further to remote sea. Our group, one of my PhD students, took part in the 32nd Trans-Antarctic research expedition, and we took off seawater from Shanghai until the Antarctic. This is all shows the sample size. And P4A is the predominant, the rank #1 among all these water samples. And the simple thing we can see is the similar spatial distribution, the spatial trend of P4A and F53B, although the concentration of 53B was much lower than P4A, but they show exactly the same spatial trend. And at the size very close to the Antarctic, their concentration was almost similar. So these results tell us that F53B could be transport with ocean current and experience long-range transport and reach the remote areas of the Earth. So why F53B exhibits some like the great potential of long-range transportation? In one of our recent studies, we investigated the transport of PFAS of the compound from water to the air with aqueous aerosol. Among all the 12 target PFAS, it's quite interesting. It's really out of our expectation that F53 exhibited the highest potential to enrich in the aerosol. So this confirms that this could be explained by the larger molecular volume of 53B relative to PFOS, and quite relate. It also might related to its polar properties. So among all these compounds, it has the highest potential to enrich in the aerosol. So after it enter the atmosphere with the aerosol, and then it will be subject to non-range transport in the air. So this is what we found for the fate and the transport of FLUOROS. And then the fragmentation and the biotransformation of these compounds. In Tahoe Lake, we collected various organic organisms from Tahoe Lake and calculate the fragmentation factor. These figures shows the relationship between fragmentation factor and the W values of these compounds. That they have a good positive correlation between them. And here is PFAS. Here is F53B. So we could see that F53B exhibits much higher fragmentation potential than PFAS. And here is another alternate PFAS, phosphoric acid. It was only slightly lower than PFAS. And for hexane, here is the hexane sulfonate, short-chain compound. It has much lower fragmentation potential than PFAS. So we are very happy to see this result because it shows lower fragmentation potential as we expected. These are then we use the in vivo use common carp as a model to investigate the fragmentation, the uptake and the elimination of these compounds in organisms, and the results confirm our the results in the field. This is the F53B. It did has higher have higher fragmentation potential, and the hexane has lower. So we the lab experiment confirmed what we also observed in the field. It seems this one, the hexane sulfonate, is good. And in the rainbow trout, similarly, we also observed the much higher. The BA and fragmentation factor is around 5 times of that. PFAS is much higher. And but the different thing is that, like PFAS, inclines to accumulate in the blood. But for the homologs of counselors of 53B, like the C2 and A2 counselors, they incline to partition in liver and kidney. So this might imply that F53B has higher because they are inclined to accumulate in liver and then induce higher hepatotoxicity. In the rainbow trout, because we very curious if they are if they could biotransform to other compounds like here or from here, the oxygen, the ether bond here. And we use non-target analysis to check to screen the metabolites in the rainbow trout. And we only detect one compound, which is the hydrogenated compound of 53B. And only here, the chlorine is hydrogenated replaced by one hydrogen, but there is no breakage here from the oxygen, the carbon oxygen bond. The transformation rate was quite low, and it's less than in total of 64 days. The total transformation was only 0.2 in liver. So the correlation was very, very low. The F53 is very persistent in the organisms. And this shows the accumulation in rat. We use this as a model, and we calculated the partition of the compounds PFAS in liver to blood, and we found these counselors of 53B has much higher binding affinity with the liver fatty acid binding proteins. So this explains the why we observed higher accumulation enrichment of 53B in animal livers relative to PFAS. We also monitor the transformation product in rat, and similar to the rainbow trout, we also detected only one compound, which is the hydrogenated compound of 53B, and this compound is also very accumulative, even though it has a higher urine elimination rate than its mother compound F53B. So these tell us that 53B is still quite persistent in mammals, although it has higher transformation rate in rat liver, which is 14% than in just now we observed in rainbow trout, which is only less 0.2. To understand the transformation mechanisms, and we conduct in vitro incubation experiments. We used take the liver from the rat and use the S9 liver S9 to incubate with another compound. If there is only S9, this reaction didn't take place. But if we add DDT to activate the reductive enzyme in the liver, the reaction took place. So this suggests that the transformation from the F53B to the hydroxylated compounds is a reductive reaction. It's reductive correlation driven by the reductive enzyme in liver. And rat, the mammals, could have a much higher activity of this kind of enzyme than in fish. So the reaction was more intensive than in fish liver. Our group also conducted several human research. In two of the research, one is quite long ago, like this, the results was published in 2013, so quite long ago, almost 10 years ago. In that and in a really recent study, we confirmed that this compound, hexane sulfate, has much lower renal clearance rate than PFAS. And in this really recent research, the concentration of 53B was similar to that of PFAS in quite general population, not occupational people. And the hexane sulfate, its concentration was also similar, was also slightly lower than PFAS. So this further confirms the wide application of these substitutes in our country. And based on the paired blood and urine samples, we could calculate the renal clearance. And this one, the 53B, its renal clearance was the lowest. It was even lower than hexane. And then based on this, we can calculate the half-life of this compound in human. For PFAS, its half-life is around 3.2 years. But for these two compounds, it's alternated, the hexane, the half-life is almost two times of that PFAS, and this one is much higher. So these suggest that the hexane sulfate, the short chain formula, has different story in human from it in aquatic organisms. These might be related to their different optic and particular different animation pathways. And the much longer half-life of these two compounds in human suggests that they could have much higher bioaccumulation potential than PFAS in human. And more attention should be paid on their human health risk, particularly of these like the hexane sulfate, because it is different. It's different from the anticipate before, although it has much lower accumulation potential in aquatic organisms. And another human study, because we are very curious why the hexane sulfate, it has much short chain. It has it short chains too. It has less carbon chain than PFAS. Why? It is more cumulative. In one of these human study, we collected like 60 pairs of human whole blood and the serum, and then calculated these coefficient Kp over D. Means these calculate the ratio of this actually refers to the bonding with human serum albumin. And this shows the result of these 60 pairs of human for the capsnate. This ratio increased with the carbon chain length as we expected. But for the sulfate, because that only two compounds sulfate were observed in these human samples, the hexane sulfate was higher than PFAS, suggesting that hexane sulfate has stronger binding ability with human serum albumin. Since this is quite very small population, then we conducted an in vitro incubation experiments using batch blood to spike the PFAS into the blood and then incubated for enough time, and the results confirmed what we observed in humans. Here is the hexane sulfate, which has the highest binding affinity with human serum albumin. Then like here is PFAS, and here is like carcinate. So these tell us hexane sulfate, although it has shorter carbon chain, but it has stronger binding affinity with serum albumin. Thus, then it accumulates more in mammals. rat and in humans. This another study investigating the placenta transfer of PFAS from mother to fetal. I remember this study was based on 100 something paired blood samples, and the results, here is the many of them, but we can focus on the comparison of hexane sulfonate and the PFAS. So the hexane sulfonate has much more efficient placenta transfer from mother to fetus than PFAS. So this again imply that hexane sulfonate could have higher human health risk than PFAS, and the cost should be paid on it. We also conduct some small research on the toxicities of these substitutes. These shows the results of comparison of the PFAS and the FVP3. The hepatotoxicity on zebrafish larvae. These figures shows the genes expression related to synthesis, uptake, decomposition, and application of fatty acid in liver. Both PFAS and FVP3, they exhibited a similar trend to up-regulate the genes of synthesis, uptake, and decomposition, but they depressed, particularly for FVP3, it depressed much stronger the excretion of fatty acid in liver. So as a result, it increased the levels of total cholesterol and triglyceride. And the obvious thing is we observed circulation of lipids in the fish liver. So these results suggested that FVP3 has at least similar or even higher, stronger hepatotoxicity than PFAS to zebrafish larvae. And I think the result is quite similar to what Professor Dye observed in the rat. And this also shows the immunotoxicity of FVP3. It dysregulated immune-related genes. And the interesting thing is that FVP3 exhibited higher immunotoxicity to zebrafish larvae than to embryos, which is opposite to many other studies, because we used to think embryo is more sensitive than larva to these chemicals or pollutants. So this shows that 53B has very strong immune toxicity, and we also should pay many attention to these compounds. I think the conclusions is quite similar to what Professor Dye said. We observed quite popular the occurrence of these oxalates, no matter PFAS oxalates or PFOA oxalates in our environment. And the hexane sulfate, although it has shorter carbon chain strength, and it did exhibit lower fragmentation in aquatic organisms, but it has different story in mammals and humans. It exhibits much higher, longer half-life in humans, and it also, because of its higher binding affinities with the serine albumins, and F53B, it displayed much higher fragmentation potentials in all the organisms, in aquatic organisms, rat and human, than PFAS. It also exhibits stronger potential to transport from water to atmosphere, to act as aerosol and then subject non-range transport. Although it is able to transformation, but the rate is quite low in some of the organisms, and the product of H, the hydrogenated compound, we don't know is any like environment behaviors, and its toxicities we don't know, because it is also very persistent in organisms. And one of our recent study, I didn't present here, we found actually H, the hydrogenated compound in groundwater. So these compounds might be also should pay attention to its degradation compound. And F53, I didn't, because I misunderstand the timeline of this conference. So I take out many results of these compounds from my presentation. Actually, this as a substitute of Gfos, it also exhibits hepatotoxicity and some endocrine disruption effects to organisms. So what we might learn from these results, and I think in future we need to use more state-of-the-art techniques to screen, to develop and screen chemicals, which should be more green and more better, safer compounds for our better society and sustainable society. Okay, I will thank the financial support from the National Science Foundation of China, and also thank the hard work of my students and my cooperators. And thank you for your attention.
There will be a
15 minutes discussion. Please release your mute button and ask questions. If there are any questions? If there are any questions?
Discussing the toxicity, and I wonder if there exists some except the albumin protein, which is indeed an abundant protein in serum. But I wonder if there are any other protein that may also dominate the binding effect. Thank you.
So if may I just want to repeat your question. So you said the binding affinities of the compounds with proteins like serine, albumin, and deliver fatty acid binding proteins in organisms is very important for their toxicities. Is there any other proteins?
These proteins.
Yeah, I try to answer your question. Yeah, if not, I will ask Professor Dai to ask the question. Actually, yeah, I think so. I think there are many other proteins also contribute to, because in human, in organism, there are so many proteins, different proteins. For example, besides the two proteins we mentioned just now, and there also in liver, there are also some like liver, the membrane, the proteins on the membrane, like the cell membrane, and also just now I talked about the fatty acid binding protein, but also there's something like fatty acid transport proteins, and other proteins like in the cord blood and in the muscle blood. I mean, there are so many proteins. All these proteins, I think they compete in the organisms, and which controls the final deposition of the compounds in the organisms. For example, one of our recent study, we try to understand the compounds, why they have different partition distribution patterns in the organisms. Some like to stay in blood and some like to stay in liver. So this actually is the competition of some major proteins by binding these chemicals. But of course, it's too difficult. There are so many proteins, we can only focus on some main proteins to understand what we observed. Yeah, I don't know, Professor. Yeah.
It is the first, if we conduct the binding study, we should be purified the protein. Yeah, right now we have expressed FABP in E. coli, then purified the pure protein for conduct this study. For human, we is easy obtain the HSA albumin from the commercial company. So we just do this two proteins. If you're interested in this binding affinity study, you can express protein in E. coli or other express system. Yeah.
We can have another question. Is there any questions? Okay, if there's no question, we will forward to the third speaker, Dr. Yana Liu, and the title is Instrumental Method and Gfos Structures. Let's welcome.
So, okay. Good morning and good afternoon, everyone. I'm Yana Liu. I'm currently an assistant professor at the State Key Lab of Environmental Chemistry and Ecotoxicology. So first of all, I'd like to thank Dr. Guibing Jiang for proposing me as a speaker at such a big conference. And I also thank the conference committee for giving me this opportunity to present. And I'm really honored. So now let's just start it. I'll have a review about non-targeted PFAS study for the past 10 years. First, I'd like to talk about PFAS work highlights in our lab, and then we'll go into PFAS non-targeted study. Specifically, we'll be focused on environmental methods and what have been discovered. And at the end, we will talk about little knowledge gaps. So our lab actually have done quite a lot of PFAS study, and here I just pick up some study about a new PFAS that is a F53B. It's an additive used in metal plating industry. We have performed a certain study about its national-wide distribution in sewage sludge and its transformation under aerobic condition. Its bioaccumulation potential in a food web in marine, and also the toxicity effects with thyroid hormones. So in these studies, we for the first time discovered the two chain length homologs and also a hydrogen substituted metabolite. Now let's go back to the non-targeted study. So first, let's look at some numbers. Overall, there are more than 5,000 PFA compounds have been registered in different databases. However, there are only less than 15 have been routinely monitored. Therefore, there are a lot of known unknown compounds around us. And let's on the other hand, let's look at the real unknowns. So quite a lot of studies have been performed, studied the total fluorine mass balance study, and all of them have found that the routinely monitored PFAS have only contributed to a very small portion of the total organic fluorine. And a recent study working with first-time mother serum has suggested that the proportion of unknown organic fluorine has been increasing along with time. Therefore, to really find out what are those unknowns, we use suspect screening and non-target analysis techniques to figure out what are those compounds. And these techniques, just like medical glasses, to help us look through the mist and then to see really what are in the black box. So in total, I found out 47 non-targeted studies have been done for the past around 10 years. And I think for the very first pioneer study will goes to a study performed by Dr. Jennifer Field in 2003. And in that study, she used fast atom bombardment mass spectrometry to analyze a surfactant specialty. And then in around 2011 and 2012, Dr. Zanya Treasure and Dr. Field, again, they started to use electrospray as an ion source. So overall, for all non-targeted study, most of the people have used LC high-res mass spec tandem system with electrospray negative mode. And in addition to the only full scan, we can see in recent years, we have developed quite a few different scan modes like DDA, DIA. And also we have built certain databases and a few scripts also like softwares for data processing. And benefit from the development of the method, we have now steadily moved from the original industry samples or commercial standards to general environmental samples. And in total, around 150 distinct classes of PFAS have been discovered. And among them, most have been ionized, while very few are sweet ions and kind ions. So how the non-target analysis has been performed? High-res mass spec is a major instrumentation for non-target analysis, and this is because of its high resolving power and high mass accuracy. Among the three major high-res mass spectrometer used, Q12 is the most frequently instrument because of satisfying resolving power and mass accuracy, and also the relatively low cost. So for a specific non-target analysis, first we would obtain a full scan spectrum, and then in those thousands of features, we have to first pick out certain ions which might be a PFAS feature, and then based on the high mass accuracy, we will assign the plausible formula, and then use mass fragmentation analysis to characterize the structure, and in the end to confirm the structure with the standard. In the whole process, the second step, prospective PFAS feature recognizing, is the most challengeable step. So how this is going to be achieved? There are currently two systems of strategies to be used. First is exact mass-based full scan data filtering. Therefore, we only have a full scan data, and then we try to fill out the potential PFAS ions with certain techniques. The second is based on the structure. So PFAS can produce certain characteristic fragments. Therefore, we use these fragments to try to find out the parent ion. So for the first technique, there are like 7 techniques have been used in past 10 years studies. So we can use a database to just search the ion. And also we can use strategic sample comparison. However, for this strategy, it really depends on whether we have a very good counterpart sample available. And for the rest of techniques, let's just go into one by one. The first one is negative mass defect. This is because a fluorine atom has a minor negative mass defect. However, for PFAS, it has a lot of fluorine atoms. Therefore, when they add up, the whole molecule will show a negative mass defect. And this technique usually can filter out like half of the ions. However, it can lead to false positive results because other atoms also shows negative mass defect. And then another technique we can use is homolog series, because PFAS usually present as chain length homologs, and Kendrick mass defect has long been used as a visualization tool to show the distribution of homologs. And then if we combine both negative mass defect and Kendrick mass defect plot, and also we convert the normal Kendrick mass to a CF2 based, therefore we will have a Kendrick mass plot specifically for PFAS. And we can see for different classes, they will show a very beautiful horizontal lines. And in these techniques, retention time really matters. So in a reverse phase liquid chromatography, the retention time for a homologous series will increase. And also the retention time difference between adjacent homologous should show a little bit decreasing trend. And the next technique can be used. It's called a isotopic matching. So it is really based on a computational comparison. So on the right hand, we have a computationally generated mass list based on certain molecule form. And on the right side, we have a full scan sample data. And then we use a certain algorithm to compare both data to see whether the isotope from both sides fit to each other. By using these techniques and also together with retention time and some fragments information, an author working with a fish and human serum sample filled out certain PFAS classes in this as shown in the result. And another good point about this technique is that it can be used for low fluorinated compounds. Actually, theoretically, it can be used for any classes of compounds. And the next technique that has been used is ion mobility spectrum. So ion mobility is a separation technique based on ion conformation. So the ions will be injected to mass spec. After ion source, the ions will fly through a drift tube and then get separated based on their size, size conformation, size, and also charge and shape, etc. So clearing cross section is a great important parameter used to describe this whole process. And it is a very intrinsic molecular descriptor and it's highly producible. So let's see, if we plot CCS versus mass, and we can see for different classes of compounds, they occupy a specific range to, and here we can see for PFAS, it has a beautiful slide line. And then if we look into closer, for different PFAS compounds, they will have their own very unique trend lines. Therefore, if we incorporate this information into the whole non-target analysis, this can be used to filter out the PFAS ions. So currently, it has been used as a verification tool to provide additional confidence in chemical annotation to verify whether other techniques have filtered out the correct ions. So for the second technique based on fragments, this is because of 2 points. One is for PFAS compounds, they produce very characteristic fragments. And for a second is about the instrument. The instrument can alternate between parent ion scan and product ion scan. Therefore, if we compare both scan to with the guide of fragment ion, we hope to find the parent ions. So based on this technique, there are currently 5 different scan modes have been incorporated into instrumentation. And besides that, some people have tried to use a standalone fluorine detector parallel to high-res mass spec to try to flag the retention time of PFAS. So let's now look at the first one, data-dependent acquisition, that is DDA. So in a DDA analysis, the instrument will first have a full scan. And then for the most intensity ions in the full scan, the instrument will perform MS-MS analysis for each of the ion. And then we will obtain the MS-MS spectrum for a few very intensive ions. So in this analysis, if we see a very specific characteristic fragments in a second mass MS spectrum, that means the parent ions can be found because the precursor and product ion information is very clear here. However, this only good to work with PFAS enriched samples. And for general environmental samples, we have to go to another technique called data independent acquisition, that is DIA. Very different from DDA. DIA is actually perform MS-MS analysis based on a selected mass range. So it has nothing to do with the intensity. If we set a certain specific range, this is called DIA. However, if we don't set any limitations for that range, we just fragment the whole range of ions. That is called all ion fragmentation. That is AIF. So either DIA or AIF are good to work with samples with very low PFAS concentrations. However, the parent and product ion relationship get lost here. And to facilitate to find the parent ion, some authors have tried certain small techniques. So in two studies, actually, the authors tried to run a Dda analysis. However, in the mass range selection, they select a very, very small range, like 5 to 10 Dalton. However, this really helps to quickly find the parent ion. However, in this process, as a trade-off, we have to run the same sample a few times, and also some narrow peaks can be lost. And two studies have explored the incorporation of ion mobility spectrum. So when we use the drift time very specifically, which can help to narrow down the range of parent ion. So we can see in the spectrum there below the figure. So the first one is without a drift time filtering. We can see a few parent ion comes out. Well, if we use drift time filtering, there's only like one ion comes out, and that actually is the parent ion. So a third technique can be used is about in-source fragmentation flagging, and it's a very similar. It's actually another version of AIF. While the only difference is the collision happens in the ion source, and then so in the end we will have a full scan and an in-source fragmentation scan, and then we extract the chromatograms of very characteristic fragments, and then we use these peaks as flags to direct to the retention time of parent ions. And then by inspecting the spectrum in this very narrowed retention time, we will find out the parent ion. And at the last, so there is a technique called neutral loss scan. So in this scan, the instrument will first run a full scan, a AIF scan, and then the instrument will compare both scan data to see whether there are certain neutral loss happened between the two data. And then once it found certain ones, it will run MS analysis for those parent ions. Therefore, we can actually directly look for certain PFAS which have a specific neutral loss. For example, like this actually specifically applicable for hydrogen substituted PFAS. And for a standalone fluorine detector, there are two trials have been done. The first one was early in 2012, and the authors tried to use a molecular absorption spectrometry to flag the retention time. However, it was done by an offline way. So the LC fraction was first collected, and then the detection was run for each fraction. And recently, early into this year, another online techniques have been explored. They use ICP MS. However, it was a very successful demonstration. However, the ROD was quite high. Therefore, there's still a long way to go before we actually use it in environmental analysis. So what have been discovered after these 10 years? Altogether, there are more than 150 distinct structures have been discovered, and more than 100 new molecules. And most of them are at the confidence level of 3, which means we clear about the functions. However, we have no we have very low confidence about the position of the function. And based on the major structures, I catalog them into 3 different groups. For the last group, there are only a few compounds have been discovered. Therefore, we just will skip that and go into the first 2 catalogs. So for the first catalogs, it's about PFCE, PFSE, and alcohols. So we can see very clearly most of them have very similar new compounds. So they can be hydrogen substituted or have an ether insertion. Also, there can be double bonds or have a chlorine substitution, etc. And also, for many compounds, they actually combine the different this kind of functional groups. So what I really want to draw your attention to is about alcohol here. So it was characterized as a unsaturated perfluoro alcohol, sorry, has been discovered in a few samples. However, early in this year, a paper published to point out that these ions may have actually been in-source rearrangement ions from PFCA. Therefore, this actually put a question mark for other alcohols we have found out. Therefore, it reminds us to really look back from time to time to really confirm what we found are real ions, not artificial ions. And then about telomeres and precursors. So I know there are quite a lot of different structures. However, if we just first ignore the fluorine part and also the sulfine part, if we just look at the alkyl part, so they can be actually cataloged into 3 groups. So in the circle one, that is zwitter ions with a acid group and with an ammonia group. And also they have the ammonia compounds and also they have acid compounds. And this compound is a very, very large group of class, and they have actually been all found in AFF samples. And these are the 4 studies which have been performed to find out those ions. And very similar with precursors, these are the regular ones, and then these are the new compounds, really new compounds. And very similar, they got certain zwitter ions and cations and anions. And this actually shows all the possible structures identified in the AFF samples. So what about the knowledge gaps? So, well, along with the ESI negative MS method approach to mature, the non-targeted method for ESI positive MS and GC-MS is nearly a blank field now. So this may be partially because the ions in positive mode cannot produce very characteristic fragments. And in a study recently being performed, the author pointed out that in WWTP effluent, the neutral portion of the unidentifiable organic fluorine actually takes up to like 50%. This reminds us in the future, maybe more studies have to be performed in these cations and zwitter ions. And also have to be cautious about the possible false positive in full scan and false negative and in fragmentation scans. So we just talked about the in-source rearrangement about a perfluoro alcohol, and also some techniques have actually been proposed to really differentiate ions to confirm the ion, whether it's a parent ion or it's a in-source fragmentation ions. Like what have been done by Mark Straner, they proposed for PFCA in gas phase, they actually can form certain adducts or dimers, and this can help. And also, I'd like to draw your attention to isomers. A lot of studies have actually mentioned that they discovered isomers of new compounds. However, most of that only take one peak and do the fragmentation, and that's all. However, I have actually seen that in a group of isomers, if you fragment all of them, not all of them are actually fluorinated compounds. Therefore, we have to be very cautious about that. And next, about instrumentation comparison between different labs and different vendors, because despite that many non-target study have been performed, there is no very many study about the data instrument comparison between different labs. Also about the QA, how a QA QC can be processed, and some terminologies, and also what can be reported in a study. From this perspective, I'd like to address the importance of chromatogram. So not many studies have reported the chromatogram, however, which can really help to eliminate false positive and also help to find isomers. Currently, the European NOMAM group and also a US BP4 non-target group, they have been working on instrument harmonization. And well, databases based on standards are really of high values. However, with so many compounds has been discovered at a very quickly rate, we propose to use certain in silicon databases to actually include more information like CCS. With many compounds being discovered very quickly, a next big question faced us is how about their safety? Therefore, for semi-quantification and chemical pre-authorization is also on the table for us to consider to see whether among all of this, what kind of compounds are really hazardous. So I'd like to thank Dr. Guibin Jiang and Dr. Ting Ruan for help me to prepare this, the slides. And also I'd like to thank Dr. John Martin, who is my PhD supervisor. I actually started my non-target work in his lab and a great supervisor. So with all of that, I'd like to finish my talk and like to take any questions you may have. Thank you.
There are 15 minutes section for questions. Is there any questions, particularly online? Or at this exhibition hall?
Hello. Hi, everyone.
Hello.
Yeah, good morning. Well, thank you very much for the wonderful presentation. I am Pavel, and I'm currently in the University of Luxembourg. And in part of your presentation, you talked about fragment directed, that's in-source as a method, or in-source ion as a method of identifying PFASs. So you specifically talked about the use of chromatograms, comparing chromatograms with the retention times of the standard. I'm also working on something similar, but I have an issue. I don't know if it's is it my instrument or it's I'm not working it well, but usually the PFAS chromatogram is usually not the best. I mean, from the results I've got, my peaks are not well, they're usually not single or discrete peaks as compared to other samples such as pesticides or stuff. So how do you do peak picking if you can't quite really identify the clear peak in the chromatograms? I mean, sometimes we have double peaks, we have also broader elutions and stuff. So do you also face these challenges?
Sorry, Dr. Picking. Do you specifically ask me about the peak picking in source fragmentation scan?
Yeah.
It was actually at the very beginning. It was a very rough peak picking by done by manual. So I will just go to the full scan spectrum, and first we will identify the negative mass defect ions, right? And then that was the first filtering criteria. And then I'll go to find a certain potential ions and then check the peaks to see whether they have the very similar or ultimately the same peak shape as the fragment ions.
Okay. Quick, just a quick one again. Do you happen to know why the chromatograms of PFAS specifically are not that discrete, are not that clear as compared to other compounds?
Could you repeat your question about PF precision not clear?
Yeah, I'm just asking if you know exactly why the peaks, the chromatograms of PFAS are not as discrete as in other compounds. Yeah, it's okay. I can always type it in the chat. Yeah, thank you.
I think that this like really depends on what specific sample you are working with, right? If you got a very simple samples with got less metric effect, that could be you have a much better chance to have a good peak shapes. And also this really depends on how well you have developed your methods. Usually I think in non-target analysis, people are focused on what can be found and don't actually pay much to, don't invest a lot to about sample separation. And I think that's actually another field that we should put more emphasis on in the future to really get better separation to work with isomers. Is that answer your question?
Yeah, thank you very much. Yeah.
Sorry, we can talk about more offline. Thank you for your question.
Is there any further questions? Okay, we will forward to the fourth presentation will be given by Professor Shi Wei, and the title is Data Mining Algorithm for Identification of Per and Polyalkyl Substances. Let's welcome.
So, hello everyone. I'm Swei from Nanjing University. First of all, I would thank Professor Jiang and Professor Ren for giving me the chance to introduce my recent work about the Gfos research. Okay. 15 years ago, when I was a PhD student, I started my PFOS research under the Professor Paul Lam from City University of Hong Kong, and also the Dr. Yamashita from the AIST Japan. At that time, I analyzed some PFOS like P4A and P4s in the sediment cores, and another group mate called Neil Young also analyzed some P4s in the blood samples, and this blood samples was also collaborated with Professor Jiang. So that was the maybe the first ESMT in China. During the past 15 years, I continued my work on the PFOS research. Now my research focuses on the non-target analysis. Today, my presentation is the data mining algorithm for the identification of per and polyfluoroalkyl substances. During the persistent and wide distribution and the toxic of the PFOS and the P4A were listed in the POPs convention. So there are a lot of substitutes were produced and discovered in our environment, such as Gnex, Adona, and F53B, which Dr. Dda and Professor Dda and Professor Zhu also introduced these chemicals. So more lower substituents have been produced without structure information that are treated as confidential business information. So the discovery of emerging PFAS is a hot topic in environmental science. However, discovery of novel PFAS is difficult work. Firstly, many substituents will enter the environment. At present, more than 7,000 PFAS were in our market, and these PFAS can also transform to the transformation products. These unknown substituents and the potential PFAS transformation products are in our environment without any structure information. And also, these novel PFAS were always with low concentration environmental samples with complex metrics. So it is a good challenge to identify this emerging Gfos. The current chemical analysis we call target analysis depends on the chemical standards. We can analyze the compound 110 to 100 of compounds with the emerging of high resolution mass spec like QTOF and Orbitrap. Two new strategies were proposed in we called suspect screening and non-target screening were more popular in the chemical analysis. The suspect screening depends on the chemical list, but the database is very limited. This screening can analyze thousands of compounds, while the non-target screening can analyze any compound with response without any prior information. However, it is a time-consuming and difficult work. So with non-target analysis, the problem on identification of emergent and unknown Gfos will be solved. The non-target analysis has become an important tool to discover toxic chemicals. In last year, in the science report, a report that the EPA researchers used the non-target analysis to identify the chloro substituted fluoro carboxylic acids and identified the Soviet company as the source. And this year, the non-target analysis was used to identify antioxidant 6-PPD in tires, which was the cause of the death of American salmon. So the non-target analysis is a good choice for analyze the people. But how to acquire the target Gfos from thousands of peaks is a hard work. Sometimes we are lost in the big data, so we need a data mining algorithm, data mining of Gfos. So this method should be high coverage, sensitive, high throughput, automatic, and with low false positive rate. So we are trying to develop a new method for the Gfos analysis. Excuse me, can I remove the? Okay, so I will introduce the non-target analysis, NTA. Here, there are 4 procedures for the non-target analysis, including the sample treatment, instrument analysis, data analysis, meaning the peak picking, and also the structure identification. My group focuses on the data analysis, peak picking, and the structural identification. So how to screen out the Gfos, the Gfos peak from thousands of peaks, and do the identification of the structure of Gfos is our key job. As you know, so before introduce the data mining algorithm for the Gfos, I will introduce some instrument analysis of the non-target screening. As you know, the exact mass, the mass 2 spectral and the retention time is very important to the structure identification. So, and the mass 2 spectral is the most important structure information. However, the current non-target screening cannot acquire it for all the Gfos peak. And just now, Dr. Liu also talk about this. So most of the researchers acquired the peaks using the data-dependent acquisition model, DDA, and it can obtain the peaks with only with higher intensity different instruments maybe have the different peaks. Some can get the top 3, and some can maybe the biggest maybe top 20. However, the data independent acquisition model DIA offers a lower way to acquire the mass 2 spectral of PFOS with low intensity and improve the number of identified the PFOS. All the peaks can be acquired, and it is very helpful for those peaks with low intensity. Here I show the acquisition window for the DIA. Here we use the SWOS by the AB company to enhance the performance of the DIA. Using the SWOS technology, we can automatically adjust the acquisition window width, and we can also reduce the interference between ions, improve the quality of mass 2 spectrum. Then we use the dual convolution algorithm and compare them, mass 2 deck and the coral deck. From the result, you can see that the coral deck can purely the PFOS mass 2 spectrum acquired by the DIA. Here is the result of the DDA and the DIA SWOS. We can see that both the methods can get almost the similar total peaks. However, the DIA improves the number of the mass 2 spectral and the identified PFOS. So with the enhanced instrument analysis, we can do the data analysis of the PFOS. Now I will introduce the data analysis peaking for the PFOS. The current method for identification of PFOS are listed here. Target analysis depends on the commercial standards, and the number of analyzed PFOS is very limited. Most target analysis are using the mass defect and need to manually screen out all the PFOS peaks. So it is a hard working and low efficiency. And also this process will be interferenced by the peak from the matrix interference. So we need automatic method or software to screen out the PFOS peaks. So just now, someone also asked this question. So we proposed a new method. We called it multi-dimensional characteristic driven mass spectral driven non-target analysis, MC-driven NTA. So for PFOS, we can choose the repeat structure unit, the PFOS congeners, and the diagnostic fragment ions to do a combination. Then we can use this rule to do the PFOS screening. Here I showed some typical structure unit and like CF2 and also the fragment ions here. Then we transform the rule to an automated software. Here is the multi-thread algorithm structure. Then we can do the PFOS screening automatically. We also developed an anti-interference module to reduce the interference by the peaking. Also, we can reduce some interference by the dimers adult ions. Here I show an example to evaluate over new methods. We choose the wastewater samples to do the identification of the PFOS. By using over new methods, the time of the data analysis reduced to 1 hour from 1 month, and the number of the identified PFOS increased by 7 times. Traditional target analysis can only analyze legacy PFOS, maybe only 10 to 20 PFOS. However, using over new methods, we can analyze hundreds of PFOS. Among these, we found 37 novel PFOS, which was firstly reported in samples, and by using the anti-interference module, we can reduce the most interference. 90% interference peak will remove thousands peaks to 100 peaks. With this MC-driven NTA, we can find most of the peaks, but it is a manual work. It depends on our knowledge. We should know what is the structure unit and the fractal ions of PFOS. But sometimes it is a knowledge-driven work, but it depends on our previous experience. So sometimes we may ignore some laws maybe which were not covered by our previous experience. So we want to do some automated work for this. And then we use the data-driven analysis for this PFOS analysis. Here we have an assumption here. Similar structure modules may have similar fragmentation rules. So PFOS should have similar structure. In that, similarity algorithm SSN to do the structure cluster analysis. Then we can find those PFOS peaks. Then we built up a molecular network between PFOS and non-PFOS with the SSN with the SSA. We choose 60 mass spectral of the PFOS and the 700 mass spectral of non-PFOS. Then we compared the result to choose the best SSA. Here I show the result of the different SSA. Finally, we find that the ratio algorithm have the lowest false positive rate. So with this SSA, then we can build up the network from the here. Then you can see that the PFOS were separately from the non-PFOS, and we choose two PFOS loads here. You can see that their structure was very similar, and the spectral was similar. So they are very close in our network. With this SA, then we can set up the PFOS networking-driven non-target analysis. We choose the long identified PFOS as the seed PFOS based on the spectral similarity, and the network analysis. We can do the label PFOS screening. Then we can find some new PFOS. Then we iterated this process continuously. Then we find some new PFOS, new seed PFOS and new PFOS. The right side, we show a typical PFOS network in samples. And then we use the same sample, the wastewater samples, to do the comparison of the two methods, PFOS network and the MC-driven NTA. Compared with MC-driven NTA, PFOS network-driven NTA increased the number of identified PFOS by 3 to 4 times. So now we collected most of the PFOS peaks in our samples, but we only pick them out. But how to identify the structure is still a big job. There are several ways to identify the exact structure of the PFOS. The first way is the manual identification, which is low efficiency and the experience is the main technology threshold. The second is the database search, which is fast, but there is limited PFOS spectral. The third one is a prediction model, which is also fast, but most prediction model is about the metabolomic analysis. So it has the poor applicability of pollutants and low accuracy. So we want to development over PFOS AI to identify the PFOS with the mass spectrum. Here we want to firstly we want to build a PFOS AI for the long PFOS without the mass 2 spectrum. Maybe here long means the long unknown. Yes. So we choose them. So we built up a mass 2 spectral database using 189 PFOS, which was from the was our commercial standard and also some open source. Then we also build up a molecular structure database. More than 60,000 PFOS. We collected their structure unit from the PubChem, US EPA, and OECD. Then we use a machine learning method to do the model training. Here is the model training phase and the parameter optimization. For the spectral, we use the we use the SSA to do the spectral fertilization to get a vector of PFOS. And the structures, we compare the different fingerprints. Then we get the structure fertilization to get the fingerprint of our structure. Then we use the machine learning method. Here we compare different machine learning method. Finally, we choose the SVM to this modeling. Then we train this model for the prediction. Here is the model application phase. Then we have a real sample. We do the mass 2 spectral fertilization. Then we use the training model to do the predict fingerprints. And then we calculate all the PFOS PubChem from the PubChem. We calculate their fingerprints from the molecular structure. Then we compare over predict fingerprints with this fingerprints. Then we do a ranking score. Finally, we will give the candidates the ranking score. Here is the model verification phase. Finally, when we compare with other existing platform, not only the top 1, but also the top 3, top 5 candidate search, the accuracy of our model is better than the existing platform, including MFID, Series 4, and the MedFrag. But this model is still depends on the database like PubChem. We need to do the candidate searching. So now we are doing a more difficult job. We call it the unknown PFOS generate model. We also use the mass 2 spectral database of the 189 PFOS, and also the molecular structure database from the PubChem. Then we using the data enhancement because the data is limited. So we use the deep learning algorithm. Here we use the new model we call transformer model for the generator of new PFOS. Then our PFOS AI structure generation model was trained by the data. Here I show the process of the how to generate some new PFOS. You can see that with the increase of the rounds of the model training, the predicted structure was greatly consistent with the real structure. Finally, you can get the predicted structure of our novel PFOS. Here I will give a summary of our results. We use the dry and the cortex to get the mass 2 spectral Then we use MC-driven NTA and network-driven NTA to pick out, to screen out the potential P-force peaks. Finally, we use the mass database to do the P-force ranking. If we want to find some novel P-force, we use the structure diagnosis P-force AI model to do the prediction. Overlap has established an emerging contaminant analysis joint lab with Angelin and provide us two QTOF instruments, and we also have the AB QTOF and the thermal orbitrap. I was also employed as a global mass spectral software development consultant by Angelin. Overlap was also invited to join the international joint comparison test of non-target analysis in last year. Next, I will talk about the discovery of novel P-force in real environment. With over new methods, more than 120 emerging P-force were detected in air, water, and biological samples, of which more than 60 P-force were firstly found. These P-force were included by the US EPA and the Norman list. And we performed a national municipal wastewater. The average proportion of emerging P-force exists at 70%, and the existing process cannot control the emission of emerging P-force. So the emerging P-force have been widely detected in wastewater in China, and the removal rate of existing process is low. Also, a lot of P-force were detected in air, especially for the gas phase. Not only in the environmental samples, a lot of lower P-force have exposed to human and transferred to the fetus, and early exposure risk assessment of lower P-force is necessary. We also use this method to do some metabolomic work. You can see that using the network analysis, we found more than 200 metabolites related to P-force exposure to the high exposure group. Then I will introduce the application of the NTA in environmental management. This method can also do the source analysis of characteristic pollutants. Here is an example to do the source analysis of lower P-force in air. In air, we found that the chloro ether P-force in the air samples, and by comparing the mass spectral fingerprint of our samples with the chemical production fingerprint of the surrounding manufacturers, we find the only source of these novel compounds, the sorbate complex, which is also consistent with the report on science in the same period. Another application is analysis on the sources of illegal discharged wastewater, because there are many chemical manufacturers in the industrial park, so it is difficult to trace the source by the target analysis. So we use non-target analysis by comparing the fingerprint of the samples with the chemical production fingerprint. Finally, we found the company X contributed most to the discharged water, and the results were confirmed by the government. So this method was used to identification the risk of the chemicals in chemical industrial park, and the risk chemicals P-force and P4A were identified in Jiangsu province, and these were adopted by the Ministry of Ecology and Environment, Chinese EPA, to provide technical support for the list of priority chemicals. At last, I will show the research on other emerging contaminants. This method can not only detect the lower P-force, but can also find some other novel compounds. Here we show an example on the nanomaterial. We do the identification of toxicity degradation products from the carbon dots. more than 1,400 kinds of photo degradation products have been found in the photo degradation of carbon dots. But how to analyze the thousands of chemicals is a big job. But with our new method, we can do this work. PEG homologs and degradation products containing benzene substructure were revealed by the MC-driven MTA. And the 499 toxicity degradation products were identified through the toxicity correlation network analysis. In the past 10 years, we built a high-resolution mass spec database. The database contains more than 20,000 chemicals, which were from the in-house databases, commercial standard open source data, literature, because they come from different sources. So we developed a program to do the auto searching using the Python based on the spectral similarity. So using our software and the database, we can improve the accuracy and the efficiency of the structure identification. And with this data, we also do some the chemical prediction model using different AI model, because the data from all the substance were quite different from the PFOS. We choose a different model. Here we choose the neutral network model, which is similar to the AlphaGo. Here is the visualization of learning process of unknown structure generation, and the results showed that for some groups, for some group of pollutants, our result is better than the existing plant form. However, because the compounds were quite different, so we need more data set to do the training. Here I showed our new platform for the long-target analysis for the pollutants. We called it MassGo. This platform contains 4 modules: MassFlow, MassDB, MassAI, and MassVisual. Here I show you the some function of our platform, but it is in Chinese. Maybe later I will develop some English version. Here is the MassDB for the database. You can do the quick search of your samples with our database. Then here is maybe using our software, and we can give you the candidate results. And the MassAI, you can improvement your fragment iron or the smiles. I will give you the candidate of the prediction result. The MassFlow is for the picking and the pre-treatment of some data. Now we have 8 groups picking pollutants, and we also do some MassVisual. We have the different visualization of the data. Here, finally, I will thank to my students. Now I have 3 groups. One is the long-target screening for environment group, and also the environmental health group, and the last is the AI group for some data mining work. And also, I will give my thanks to my university and also the collaborators, and also thanks to the engineering company and the Solomon company. They provided us the instrument and also the database. That's all for my presentation. Thank you.
Thanks for the interesting presentation. Is there any question? Especially online, is there any question? Then I will ask a question. I noticed that you have used the MS to structure similarity search and the AlphaGo to make a database, which showed a very excellent performance compared with other search engines such as CSI Finger ID and the Medfrag. So can you give some more details on why this algorithm could have such a excellent performance, especially compared with the CSI Finger ID, because this platform is considered as the best machine learning algorithm currently for the mass spectrum. Thank you.
Okay, thank you. So first of all, it depends on maybe the training data set. The existing platform like Cirrus, maybe which is always the best one to do the prediction of unknown chemicals, but their training set is most from the GNPS and other metabolomic database. So it is only for it is better for those metabolomic analysis. Then we input over Gfos data to this platform. We find it is not very useful for the pollutants because the structure was quite different from the pollutants with metabolomic analysis. So then we have because we built a large high-resolution mass spec database containing more than 20,000 data sets. I think the data set is the most important for the training. And so we do a lot of work to collect this data. So that is the first reason. The second reason may be it depends on the target chemicals. What do you want? Which you want to do the prediction? Now the best prediction model, the best chemicals is the Gfos, because we put a lot of work for these chemicals. We know how to fragmentation of these chemicals, then to do the prediction, how to change their structure to the fingerprints and also some vectors to then we use the different machine learning and also some deep learning to do the prediction of the Gfos. And we also have maybe the biggest Gfos data set. We have about 200 Gfos high-resolution mass spec with different energies. So I think we bought all the commercial products of the Gfos in the market. So I think this over platform is very suitable for the Gfos. But for the other, we are still include some other different other groups of the pollutants, and we find that maybe for some chlorine and bromine compounds, this work will also effective. But for all the pollutants, not only over platform but also the other platform is not very effective. So this work is still ongoing. That's all.
Okay, thank you. Is there any question? Then it will be the end of this section. Thank you all the professors to give a very exciting and informative presentations. Thank you all of your the attendees to hearing. Thank you.